All right, finishing up section 1.6. Okay, let's look at some conditions concerning the invertibility of a matrix A. Again, this ain't the last time either. Theorem 1.16 says, let A be a square matrix, n by n matrix. The following are equivalent. AX equals B has a unique solution for every B in Rn. A is a row equivalent to the identity. A is invertible. These three we've seen before. Here's a new one. The column vectors of A form a basis for Rn. So basis is the new idea in this. We've seen equivalents of these first three in the past. And I say again, think how you'd establish each of these. How would you show A is invertible, for example? You'd augment A with the identity matrix and you'd row reduce it. It'd work and you'd find the identity if A is row equivalent to the identity, if you can reduce A down to the identity, in other words. What's up with this unique solution thing? How would you solve this system of equations? I'd take A and augment it with the vector B and row reduce. And if it worked and we got a unique solution, then that would happen because how about A is row equivalent to the identity? We get the identity out, we just read off the values of those unknowns. So this mathematical gibberish stuff ain't so gibberishy if you think how you do this. And it's always row reduction, reduce row echelon form or row echelon form, preferably reduce row echelon form. And in the terms of getting unique solutions, finding identity matrices somehow or other, which is the same thing that happens when you look for inverses. So down here, the new claim is the column vectors of A form a basis for Rn. Well, you know those column vectors live in Rn. The previous theorem, Theorem 15, said we have a basis for a span if and only if this particular linear combination implies all the coefficients are 0. Okay, down here, we could take B to be the 0 vector. Remember AX, note 1.3.a. AX is a linear combination of the columns of A. So you're saying linear combinations of columns of A can take on any value B in a unique way. So that gives us that any vector B in Rn is a linear combination of the A. In other words, the columns of A span all of Rn. All right, that's half of what we needed up here. The columns of A span Rn. They're a basis if we get this linear independence. So back to the vector B. If we set this equal to 0, we get AX equals 0. We'll know, if I assume this first condition, say, this has a unique solution. Well, if the B vector is a 0 vector, a solution is the X vector equals a 0 vector. That is, all those coefficients up here, represented with subscripted R's up here, all those coefficients are 0. And that must be the case if that's the only solution to the system of equations when I put the 0 vector in for B. Then Theorem 1.15 will imply that this observation will show you that the column vectors of A form a basis for Rn. So there's a verbal walkthrough on the proof. The only new thing to be established is that this last claim is equivalent to the previous three. The first one's the one to focus on in light of Theorem 15. Okay, let's look at page 100, number 22 again. All right, taking a slightly different angle on this. In part B, what we're doing is we're asked a question, use Theorem 1.16, we'll look at it again, to determine whether the set of vectors given here is a basis for the subspace of R2 that these vectors span. Okay, so we've got vectors, we're looking at a spanning set, and the question is, do we have a basis? Let's take a look again at Theorem 16. It says, well, the column vectors of A form a basis of Rn. Ooh, so let's take those vectors and put them in a matrix A as columns. Then we can talk about this. We know this to be the case if and only if any of these other things hold. How about this one? A is row equivalent to the identity. Can you take A and row reduce it to the identity? If so, then yes. Basis for its span is what we'll get out of this one. If not, then no, not a basis. So that's what they mean by use Theorem 16. Mechanically, what we'll do is create a matrix A, because this question doesn't involve a matrix A. You like matrices, you're learning a lot of stuff about matrices. So it will be common for us to take a question in one setting and set it up as a question involving matrices, and that's the plan here. So take these two vectors, let's put them in matrix A as columns. All right, it's not the last time we'll do that. Theorem 16 says the columns of A form a basis for their span, a basis for R2, if and only if A is row equivalent to the identity. All right, that was part 2. So we've got a basis if that matrix A is row equivalent to the identity. Now this is the same kind of manipulations we did previously. Previously we set up a system of equations and we used Theorem 15. Here we're dealing with similar manipulations in terms of the matrix, but we skipped over the system of equations in this one. This is a super useful observation. We're determining if we have a basis just by putting vectors in a matrix as columns and row reducing. Okay, so here's matrix A. The vectors went in as columns, right? First vector is -1, 1. First column is -1, 1, right? Second vector is 1, 2. Second column is 1, 2. Unhappy coincidence. If I put these in as rows, I get the same numbers. But that's because of the components of the vectors. That's a coincidence. These vectors have gone in as columns because Theorem 16 talks about spans of columns of the matrix. So these went in as columns. Just a coincidence that, gee, if I put them in as rows, we get the same collection of numbers. Coincidence, that won't always happen. The numbers are pretty here. All right, so we do our row reduction thing and find out that indeed A is row equivalent to the identity. All right, well then Theorem 16 says you got yourself then a basis for the subspace of R2 that it spans. There's two vectors, so they must span all of R2. Okay, so to test a collection of vectors to see if it is a basis for its span, we're gonna do that quite often. Put those vectors in a matrix A as columns and see if that matrix is row equivalent to the identity. So a question upstairs about basis becomes a question then about row reduction. And you're good at row reduction. So much of what we do is based on row reduction. Okay, let's shift the gears a bit again and look at systems of equations. This time, considering maybe a coefficient matrix in a system of equations that isn't square. We've discussed a moderate amount of systems with square matrices, especially when we talked about inverse matrices. Only square matrices have inverses. And Theorem 17 says, maybe more the corollaries that are useful. And we'll see if we can't make sense out of this in the same way, thinking about how you'd solve these systems of equations, augmented matrices and row reductions, how you'd solve them. Let A be an m by n matrix. The following are equivalent. Each consistent system, AX equals B, has a unique solution. All right, how would you find that unique solution? M by N matrix, no longer a square matrix. How is it you get a unique solution out? Well, you take A, augment it with B, and you would need, see if this makes sense, you'd need a pivot in every column. If you had pivot-free columns, you've seen those correspond to free variables. We are dealing with a consistent system, right? If it's an inconsistent system, then, well, you know what's going to happen there as well, but we're in the setting of a consistent system. All right, well, what's going to happen when you solve this? Either we'll have a pivot in every column and get a unique solution, that must be the case, or we'd have pivot-free columns, and we'd have free variables, and we get infinitely many solutions. Think how you solve them. So saying, we're claiming each of these three things is equivalent. Saying this first one, we get AX equals B has a unique solution. Whenever we deal with a consistent system, you must have this matrix A to row reduce in such a way that every column has a pivot. That's how you find the unique solution. You solve for X1 equals, X2 equals, and so forth. Second situation, second condition, is the reduced row echelon form of A consists of the n by n identity matrix followed by m minus n rows of zeros. Okay, yeah, that's what would happen up here. Every column would have a pivot. First column, 1 followed by a bunch of zeros. Second column, 0, 1 followed by a bunch of zeros, and so forth. Now, you might run out of columns before you run out of rows, and that's what they're saying here. And down at the bottom, have a few extra rows added in. Well, if we've got a consistent system, those extra rows have to be all zeros to the left of the partition when we make the augmented matrix. And if it's a consistent system, have to have zeros to the right as well. So they correspond, if we were to convert it back into a system of equations, those last few rows correspond to 0 equals 0. 0 equals 0. So nothing wrong with that. No information there either, it turns out. So it should make sense that these first two are equivalent. The last talks about bases again. The column vectors of A form a basis for the column space of A. All right, how do you feel about that? Well, we take these column vectors. The column space of A is the span of those vectors, so it becomes a question of I want to say linear independence. It becomes a question of, so we'll apply Theorem 15. Can't apply Theorem 16, it only applies to square matrices. I've got to go back up here. We'd have to apply it to this. This, think of it as coefficient times first column plus coefficient times second column, blah, 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 plus coefficient times last column equals 0. That would have to imply that those coefficients are 0. Hey, you know, whenever you consider a system of equations, AX equals B, remember, note 1.3.A, this on the left-hand side, that's a linear combination of the columns of matrix A. Hey, that's what they're talking about down here. So the column space is the span of the columns, back to Theorem 15. So we got the span part going on. How do you get the basis part going on? When you have a linear combination equal to 0, you must have zeros as the solutions. All right, well, back to Theorem 17. Consider this system of equations. If we put the 0 vector there, that has a unique solution. Well, that solution is a solution of all zeros for coefficients. In other words, Theorem 15 holds. So having a unique solution is intimately related to the situation here. Of course, if we've got this as a system of equations, no, we could take R1 through R sub k equal to 0. The statement here is that you must take R1 through R sub k equals 0. That is, there's only one choice for these coefficients, and that choice is all zeros. Yeah, that's what we have here. there's only one choice for those coefficients. There's only one choice for these coefficients, the components of x, when we choose, say, b equals a 0 vector. It's consistent when b equals a 0 vector, has a unique solution. Those coefficients must be 0. Then you got yourself a basis. Theorem 15 gives you the basis stuff in this one. All right. So let's see, anything useful computationally here? Could you check and see if the column vectors of A form a basis for the column space? I guess maybe we try to use part 2. Row reduce A and see if you get an identity matrix, a pivot in every column, followed by a bunch of rows of zeros. So that's how we could illustrate or employ property 3 by using row reduction and property 2. Some consequences are, and this has likely crossed your mind already just from your massive experience with solving systems of equations so far in chapter 1. Corollary 1, fewer equations than unknowns, says, in a linear system, ax equals b, that's consistent, and has fewer equations than unknowns, has an infinite number of solutions. Such a system is called underdetermined. All right. We can justify that with some of this Theorem 17 stuff. How about better yet, think about it. Fewer equations than unknowns. All right. You're given that it's consistent if the system is consistent, so it has a solution. Question becomes, does it have a unique solution or more than one solution? Claim here is it has infinitely many solutions. Well, why is that? Fewer equations and unknowns. Create the augmented matrix. What happens when you start row reducing? You're going to get a pivot in every column. You get a pivot in every column, you got a unique solution. There's fewer equations than there are unknowns. If you like, in matrix A, there's more columns than there are rows. Or there's, maybe I should read it as fewer rows than there are columns. Pivot is the first non-zero entry in a row. How many pivots can this matrix have? Well, it could have one in every row. But there's more columns than rows, so it can't have one in every column. Well, if it can't have a pivot in every column, if it has pivot-free columns, there's free variables and infinitely many solutions. So that's the way to think of this, provided it's consistent, and I don't know how you're going to know the system's consistent until you try to row reduce it. So maybe computationally, this hypothesis of consistency may not be particularly useful, but the behavior is not surprising at all if you think how you solve these. Row reduce, every column has a pivot, unique solution. Pivot-free columns, free variables, provided it's a consistent system. Second corollary deals with homogeneous systems of equations. A homogeneous linear system, ax equals 0, having fewer equations than unknowns, has a non-trivial solution. Yeah, it's got, apparently by the previous result, it's got infinitely many non-trivial solutions. Remember, the trivial solution was the solution x vector equals a 0 vector. Yeah, it's got infinitely many non-trivial solutions. Second claim, a square homogeneous system, ax equals 0, has a non-trivial solution if and only if A is not row equivalent to the identity matrix. Yeah, if A is row equivalent to the identity matrix, then we got a unique solution, and that would have to be the trivial solution, x equals 0. If not unique, if not row equivalent to the identity matrix, something goes wrong. Probably pivot-free columns. This is a consistent system. Yeah, it'd be pivot-free columns. That means free variables. That means non-trivial solutions, more than one solution, more solutions than just x vector equals a 0 vector. Okay, this is useful. I still don't like our definition of basis, but we're getting there. In Example 6, it's shown that a basis of Rn cannot contain more than n vectors. So the n there is the n from Rn. So the vectors have n components. That's when you're saying these vectors are from Rn. Basis means a spanning set where every vector can be uniquely written. Remember our definition of basis. So let's take a look at that one. Okay, for some notation, suppose V1 through V sub k is a basis for Rn. And let's assume k is greater than n. So we've got more vectors than n, a greater number of vectors than n. And that's going to lead to a contradiction. The claim is in a basis, you can't have more than n vectors. Okay, well, suppose you could. Say that number is k. All right, let's see what happens. Consider a system ax equals 0, where the column vectors of A are these basis vectors. Okay, how many rows will A have? Well, these vectors are going into matrix A as columns. So for every component of one of these vectors, there'll be a row of matrix A. The vectors are from Rn. Vectors are from Rn. The vectors have n components, so there's n rows of matrix A. How many columns? Well, these are the column vectors, and there's k of those. So we'll have n rows and k columns. In terms of the system of equations, that corresponds to n equations and k unknowns, where k is greater than n. So that's why it ties in with the stuff we just had. All right, so let's maybe reword it as n less than k. Same thing, same as our hypothesis. With n less than k, we have fewer equations than unknowns. Corollary 2 implies, when we were dealing with a homogeneous case, that there is a non-trivial solution to the system of equations ax equals 0. But then there's a vector we can write in more than one way in Rn, showing us that we don't have a basis. Basis means every vector can be written in a unique way as a linear combination of the basis vectors. But we could write the 0 vector in terms of the coefficients that come out of this non-trivial solution. Non-trivial means not all the coefficients are 0. And of course, we could write the 0 vector as a linear combination of these where all the coefficients are 0. What's your problem? You can write the 0 vector as a linear combination of these using all coefficients of 0. Well, duh. And using this, from corollary 2, this non-trivial solution. There it is, this non-trivial solution of that system of equations. There's a vector x, not all of whose components are 0, that satisfies this equation. Use those components as coefficients on these vectors, you get the 0 vector. That's what the system of equations means. You can't write a vector in more than one way and have a basis. So this contradicts the fact that we have a basis. This contradiction tells you that the assumption that k is greater than n is false, and so we must have the negation of that. K is less than or equal to n, cannot be more than, is how they stated it there. So this gives us a constraint on the size of a basis of Rn. It can't be more than n. As we'll see, it's going to be exactly n. We haven't defined dimension yet, but we're getting there. Chapter 2 thing. Okay, next we're going to go back to systems of equations, homogeneous systems, ax equals 0, and more general systems, ax equals b. So it's the first time we've looked at really two variations of a system of equations. We've got the same left-hand sides, the ax. The right-hand side, we're considering zeros with the right-hand side of all those equations. That is, we're considering a homogeneous system of equations. And something else. This vector b, maybe all the components aren't 0. So we're dealing with a different system of equations. So two systems of equations intimately related. This is a homogeneous system. This pretend is not. I mean, it's not necessarily the case, but that's the use that we'll get out of it. So two systems of equations, but same coefficient matrix for both. One homogeneous, one non-homogeneous. Theorem 18 tells you what the structure of the solution set of the non-homogeneous system looks like. And you're going to see some stuff super similar to this when you do differential equations and you study homogeneous and non-homogeneous linear differential equations. Linear, some of this matrix stuff, those types of differential equations could be couched in terms of this matrix stuff. So there's some overlap in D's and linear algebra right there. Okay, claim is let AX equals B be a linear system. If P is any particular solution, that's why they're using vector P, of AX equals B. In other words, we have the fact that A times vector P equals B. It's some solution. And if H is a solution to AX equals 0, so it's a solution to the associated homogeneous. So H for solution to homogeneous, P for particular solution of the non-homogeneous system of equations. Then the claim is P plus H is also a solution to the non-homogeneous system of equations. In addition to that, every solution of AX equals B is of the form P plus H. And the general solution to AX equals B is X equals P plus H, where AH equals 0, that is, H is an arbitrary element of the null space of A. Remember, all such vectors H form the null space of matrix A. Every solution can be written in the form X equals P plus H. For this particular solution P to AX equals B, plus, think of it as adding, in a sense, as oddball notation. We'll illustrate it in a second. Adding every solution to the homogeneous system. In other words, adding every vector from the null space of A. Solution to a homogeneous system, element of the null space. Same thing. That's what the null space was. The vector space of all solutions to the homogeneous system of equations, AX equals 0. All right, so let's see here. Let's go through the proof because it's computational. And hey, when you hear homogeneous and all this stuff, you're thinking 0. This is going to work because we're adding 0 to something, and that doesn't change it. That's just the big idea behind this. A whole pile of vocabulary, but it boils down to you add 0 to something and it doesn't change this something. Let's go through the proof. All right. So two things. First, let's show the P plus H is a solution of AX equals B, where we're given all that stuff. All right, let P be a particular solution to that system of equations. In other words, A times vector P equals B, X equals P is a solution. Let H be a solution of the homogeneous system. In other words, AH equals 0. Then we want to see if P plus H is a solution to AX equals B. Then let's plug in P plus H for X and see if we don't get B out. So A times X, A times P plus H. All right, we can distribute. We got nice behavior on matrix multiplication, except for commutativity, we don't have that. But we've got distribution. We've got distribution of matrix multiplication over matrix addition, if you like. Vectors are special cases of matrices. All right, so we do our distributing. Hey, what's A times vector P? Vector B. That's where the P came from. What's A times vector H? 0. That's where the H came from. So we get B vector plus 0 vector. That is the B vector. So indeed, P plus H is a solution to the system of equations AX equals B. The second claim is every solution of AX equals B is of the form P plus H. For the P vector we found above, possibly for a different homogeneous vector. That's what their wording is meant to mean. All right, so suppose Q is any solution to AX equals B. I've chosen different vector Q. With P as a particular solution, consider A times Q minus P. We're going somewhere with this, but we got our reasons. Just like before, we can distribute A times Q. We assume Q is a solution to AX equals B. So A times Q would be vector B. A times P, as above, is vector B. We get out 0. So Q minus P is a solution to the system of equations AX equals 0. Q minus P is a solution of the homogeneous system of equations. All right, we'll denote it with an H, some solution to the homogeneous system of equations, and then rearrange this to get Q equals P plus H. We assume Q was some solution to the non-homogeneous system, and we showed indeed Q is of the form particular solution we had from above plus some solution to the homogeneous system of equations. It's an arbitrary solution. Every solution must be of that form. All right. Here we had, thing minus itself equals 0. On the previous slide, we had thing plus 0 equals thing. I told you the ideas behind this are super elementary. The verbiage is the most complicated thing. Homogeneous this, particular that, column spaces, pivots, and all that stuff. But the ideas behind all this stuff are not that complicated. I think it's the vocabulary. All right, well, let's illustrate that thing we just saw with the particular solutions and the homogeneous solutions for this system of equations. The instructions are solve this system and express the solution set in a form that illustrates Theorem 1.18, P plus H type answer. Okay, we'll make our augmented matrix. We'll row reduce, first column, excellent shape, work on the second column, work on the second column some more, second column, work on the third column. We look like we're in good shape to fix the third column, and there you go. We had, I probably should have observed, we had 3 equations and 4 unknowns. So if it's consistent, then it has infinitely many solutions, more unknowns than equations, fewer equations and unknowns. This is how they stated it. But we've got down to here. Let's take this and write it in terms of an associated system of equations. So take the augmented matrix, turn it back into a system of equations. x1, x2, x3, x4 were the unknowns. So we'll get something of this form. Give me a particular solution. Okay, how about I take x4 equals 0? Take x4 equals 0, then x1 is this, x2 is that, x3 is 0, and well, I'm taking x4 to be 0. Take x4 to be some particular real number. Right? It's going to be a free variable shortly, but we're doing something different. We're looking for a particular solution. So take any value you like for x sub 4. 0, arithmetic's good with 0. You got a better idea? Maybe 30 wouldn't have been a bad idea. Would have got rid of these fractions. I'd have to do more arithmetic. I don't know, I have to move it on to the other side. Maybe that's not such a good idea. Well, it doesn't matter. Take x4 to be anything. Fractions, I might be able to avoid these if I really thought ahead, but it's more trouble than it's worth. We've got them isolated at least. Okay, so a particular solution can be found by taking, say, x sub 4 equals to 0. Okay. That produces this particular solution, x1, x2, x3, and x4 were both 0. So we got the vector P that theorem spoke of. How about the associated homogeneous system of equations? Suppose we take AX equals 0. Let's solve that system of equations. Well, it's the same coefficient matrix. We get the same thing we had upstairs, except on the right-hand side, we'd have all zeros now. If we started with all zeros, they'd stay all zeros in the row reduction. So if we looked at the associated homogeneous system of equations, we'd have this. We want the general solution to that. All right. So we'll solve for x1, x2, x3, x4. Of course, x4 will be the free variable. We knew a free variable was coming. We're going to put it in the homogeneous part, though. Let's choose to select r as a free variable in such a way that x4 equals 30 times r. Since r is any element of the reals, 30 times r is also any element of the real. So let's make that substitution. If you like, we're setting r equal to x sub 4 divided by 30. I mean, there's an x sub 4 divided by 30. There's an x sub 4 divided by 30. There's an x sub 4 divided by 6, which is not a bad thing to have with an eye on this 30. But if you like, we're making this type of substitution. Substituting in, I see the cancellation occur. All right, we'll pick up a 30r down here. x4 equals 30r. So be a little careful on that. Going to the next slide. We're plugging in x4 equals 30r. All right, that'll produce these values in terms of r of x1, x2, x3, and x4. So for the homogeneous system of equations, we get any scalar r multiple of the vector with components 1, 13, negative 5, 30. 1, 13, negative 5, 30. So the general solution, or the solution set, to the homogeneous system of equations is scalar multiple of this particular vector here. Could you have more than one scalar multiple down here? Yeah, you could have had, I mean, potentially a second free variable, and we get a second vector and a second, like an R and an S down here. Parenthetic comment, by the way, this is the null space of matrix A. We found the general solution to the homogeneous system. So, all right, so we've got a particular vector. This was the particular vector. We've got all solutions to the homogeneous system of equations. So we can say the general solution to the original non-homogeneous system of equations is all vectors x of the form p plus h, where we take this as the p vector, and we take h to be from this set of vectors. So that's what they were getting at in Theorem 1.18. A particular vector, by the way, we could have found different particular vectors. We set x4 equals 0 to get this one. We could have set x4 equal to something else and got something different. That wouldn't affect the collection of vectors we get for the general solution. They might look a lot different, but they'd be the same collection of vectors. Here we could have tweaked this and had different approaches. We could have fractions in this vector. If we just let x4 equal r, there'd be some fractions here. I buried those fractions. I didn't bury these. So there's other ways to express this as well. But what they're getting at in Theorem 18 is every solution x is of the form p plus h, where p is some particular vector. We've got this one for the system of equations, so we could have others. And h is a vector from the null space of A. It is a vector that's a solution to the associated homogeneous system of equations. So there's the p, and there's where the h's come from. Another one. Also, with an eye towards Theorem 1.18, prove why no system of linear equations can have exactly two solutions. We've only seen three things happen with systems of equations, because only three things can happen with systems of equations. We've seen them have no solutions when they were inconsistent. We've seen them have unique solutions, and we've seen them have not unique solutions. And the only time they had not unique solutions was when we had free variables. Then they had infinitely many solutions. So this isn't a surprising result. Let's go through the argument. All right, let's assume it does have two solutions. So suppose we have a linear system of equations that has two solutions. We're going to violate that of having exactly two solutions by finding a third solution. Okay, AX equals B. Suppose P1 and P2 are particular solutions and they're different. So we have exactly two solutions to AX equals B, and they are P1 and P2. All right, consider the difference, P1 minus P2. If we apply matrix A to P1 minus P2, multiply it, that'll give us AP1 minus AP2 by distribution. AP1 equals B because P1 is a solution to the system of equations. AP2 equals B for the same reasons. We get the difference of B, we get the difference B minus B, which is, of course, is a zero vector. So A times this P1 minus P2, that's a solution to the associated homogeneous system of equations. P1 minus P2, when A is applied to it, gives a zero vector. P1 minus P2, let's denote it with an H, because that's a solution to the homogeneous system of equations. All right. Oh, by the way, H, P1 minus P2, that's not the zero vector because P1 and P2 are not the same vector. So they differ in some component. They're not the zero vector, by the way. So H is a non-trivial solution. All right. Geez, Theorem 1.18 said, take a particular solution, add a homogeneous solution to it. That's going to give you another solution. So take P1 and let's add H. That'll be a solution to AX equals B, because Theorem 1.18 said take a particular solution, add a homogeneous solution. That gives you a solution to another solution to AX equals B. And you're effectively adding zero once I put the matrices in. All right, well, P1 plus H, where we've chosen H to be P1 minus P2, becomes P1 plus P1 minus P2. That gives us 2P1 minus P2. Our claim is that ain't P sub 1. I mean, if it was, then we'd have P1 equals P2. And that was part of our setup. Those are different. Also, P1 plus H doesn't equal P sub 2. Or else we'd have P1 equals P sub 2. Also a contradiction. So here's a third solution. 2P1 minus P2. It's neither P1 nor P2, yet it's a solution by Theorem 1.18. Things of this form are solutions to the original system of equations, AX equals B. Well, we said there was exactly, we assumed there were exactly two solutions. There can't be two solutions. If you got two solutions, I'll find you a third solution, contradicting the assumption that we had two solutions. All right. So our assumption that there's exactly two solutions is false. Can't have exactly two solutions. Of course, you know what happens. It either has one solution or it has infinitely many. And you know where they come from. They come from free variables, that infinitely many. All right, I think this is our last one. Let's show an intersection of two subspaces of Rn is a subspace of Rn. Let W1 and W2 be subspaces of Rn. Show their intersection is a subspace. All right, subspace of Rn. How do you show something's a subspace of Rn? It had to be closed under vector addition and scalar multiplication. If you like, it has to be closed under linear combinations. But we'll leave it in those two stages of showing closed under vector addition and closed under scalar multiplication. The very definition of subspace. So take two vectors, u and v, and w1 intersect w2. All right. That means u and v they're both in w1 and they're both in w2. Well, w1 was given to be a subspace of Rn. So it's closed under vector addition. So if u and v are in w1, then u plus v is in w1. Same thing for w2. It's a subspace, so it's closed under vector addition. So if u and v are in w2, then u plus v is also in w2. We'll get a similar kind of behavior with scalar multiples as well. So u plus v, it's in both of these. It's in W1 and it's in W2. In other words, it's in the intersection of W1, W2. And that intersection is closed under vector addition. All right, so we're halfway there. What do we need to show? Closed under vector addition and closed under scalar multiplication. So give me a scalar, let's call it R. And we'll use, I don't only need one vector this time, let's use a U. We've taken u already to be in the intersection, so take r to be a scalar. Let's consider r times u. Well, w1 is closed under scalar multiplication because it's a subspace. It was given as a subspace, so r times u is in w1. Same argument. W2 is a subspace. It's closed under scalar multiplication, so scalar R times vector U is in W2. So R times U is in both of them. So it's in the intersection, and the intersection is closed under scalar multiplication. We've got closure under vector addition, scalar multiplication. We got ourselves a subspace. So intersections of subspaces are subspaces in the setting of Rn. This is true in other settings as well, but our only setting so far is Rn and subspaces of Rn. You change this to union? Do that with W1 union W2? Maybe that's number 48. No, that ain't true. More of that later, but a union of two subspaces is not a subspace. This very much depended on being in both, this argument we put together here. Being in one or the other, in a sense, that's what you deal with when we're dealing with a union of two sets, but can't use the same argument. In fact, the union of two subspaces of Rn need not be a subspace. Before it's over with, we'll see some very concrete examples of that. And that takes care of 1.6, takes care from the video's perspective, it takes care of chapter 1. So on to chapter 2, more vectors, but this basically should finish the material that first test would cover. Have a nice day.